All right. Good afternoon, everyone. We'll get started in a few minutes. I hope you're having a good Sunday. Been not too bad for me so far. I did start my Sunday a little bit late, so I'm still drinking coffee. Apologies for that. But I'm excited to get to what we're going to do today. There are a couple things that we need to wrap up from the last session. Particularly some bugs I noticed after the session ended. I went ahead and committed them to the repository, but I'll go through them real quick. And they would have probably made our lives really hard figuring out what was wrong. So I'm glad I found them before we got too far into writing files. Hi, Chris. Welcome to the stream. Thanks for coming. I think, I don't know if it came to mind while I was streaming last week, but one of the things that was weird to me was it appeared that the nursery would read from the write-ahead log into memory and discard the log. But then there's a potential to crash right there. And then you've lost all that data that you've discarded from the log. So that is not true. And I thought, oh, well, maybe what we need to do is write a new log file with the stuff we just read, because potentially it was corrupted at the end or whatever. But that's not what HanoiDB, the original, does. So we're going to look at what it does, and it'll segue nicely into actually writing the real B tree data files, because that's what it does. It writes a file called nursery.data in the B tree format. So we'll be able to, if we go and like we make the file writer, we'll be able to take the recovery and write it to a data file and potentially inject it into the bottom level automatically. Now that, like, we haven't even figured out what the structure of levels are going to be, so it's sort of not relevant at this point. But at the very least, we can write out, hopefully by the end of today, we can write out a file that contains the B tree. And I think it'll be really interesting and kind of challenging. There are a lot of things that we need to consider, and there's a lot of code that we need to read. So it should be fun. And slightly off topic, Chris, how did your game jam go? I would love to know. I haven't caught up with your streams yet. Anyway, as Chris writes his answer, I will go ahead and switch over and we can start looking at. Oh, that sounds fun. I did see some of your isometric stuff where you made them the character and the other things in Blender, and then exported them in that perspective, and that was really cool. So nice. I'll see if I can catch up maybe tonight. Okay, I want to talk about these two bug fixes. Also, congratulations, Chris, for participating. I know that's a challenging thing to do. I did at least one hackathon type thing. I think it was Rails Rumble way back in the day. And that was only 2 or 3 days, not a whole week. Okay, so there were some bugs left over from what we did last time. The first one is that, remember we had to switch from getting the marker tag, like the boundary tag of entries. We had to switch from it being at the beginning of the entry to being at the end. for various reasons. But one thing I didn't do is I didn't put it in the right place. So what we were doing here on the left in the diff that was changed, we were pushing the tag onto the end, and that would change because we're slicing from 8 to the end of the vec. That would have changed the CRC, and the CRC is only supposed to be over the body, not including the tag. So putting that at the end after the CRC has been computed fixes that bug. Okay, and then the last one was related to that. It was, we actually were adding the tag end on the length computation, but we don't need that for this because we're always going to be inserting that byte after we've emitted the entry. Yeah, so we don't, the encoded size of an entry doesn't need to include that. Oh, right. So we actually put it here at the top of that function. So this was double counting the tag. Okay. So those are 2 bug fixes that I did after the stream ended. Let's get back into the code. So want to quickly review where we were. This is the nursery. Remember, we spent a lot of time here in recovery. And this was going to return nursery data and use size, which was the total size of the nursery. Right, so we were reading entries from the file, and the entry read function gives you back a size. And yeah, okay, so the other thing that we have to do after we do this recover is we need to write out the contents of this nursery to a data file. And that's so that you can continue doing the append only as new entries are added, but you don't lose the contents of that because you've truncated the log. The contents that you've just recovered, you don't lose it. So how does the original HanoiDB do it? Okay, so we've already looked at this a bit, but remember, if it finds the log file in our data directory, then it'll do this do recover function. And this is the part that we've implemented so far. So read nursery from log. There's this other kind of, I don't know, inconvenient is not the word, but like suspiciously named function called finish. If we go down and we look at what it does, and I can do this, that'll be a little easier. Where did it go? Finish. There we go. Okay. I still don't have LSP figured out on Zed, so I don't know that Darren comes to my stream, but I know that he has worked on that, so I would love it if you'd help me at some point, Darren. Anyway, okay, so finish is basically, you know, write this to a B tree and delete the nursery file. So this says, you know, if we've got a log file open, close it. So this function is used both in this recovery phase as well as when you want to start a new nursery, because you need to flush and inject the contents of the nursery into the bottom level. Okay, so first close the log file, and then if there are entries, so this is basically if count is greater than 0, kind of a weird way to express it, but okay. Then the idea is we'll write this nursery data file, and they're using this HanoiDB writer, and it basically gives this data structure which lets you inject. So it's kind of a similar idea to the nursery in a way. So we might be able to make a writer struct which holds the file, And the B tree size is min level, and then we'll have to definitely look at what HanoiDB writer does. But then it just loops over the contents of the data that was just recovered or was concurrently being written, and adds it to that. Now, since this, GB trees in Erlang and B tree maps in Rust are ordered, you're always going to add keys in the order that they should be in the final file. Okay, so then they close that writer, which basically closes this file, and then tries to inject this into the top level. So this is sort of Erlang stuff where it's like making a call to that level, like, here, take this file. And then there's some, trigger merge stuff. And then it deletes the log file. So one of the things that we could change here in our recovery is that, here in recover, we should, after we've read these, so we've got the nursery data, we can do this remove file, etc., right? But we should take this and inject it, like loop over it, inject it into a writer of the data file. So right, that's not what I wanted to do. So we need to look at HanoiDB writer and see what it does. Excuse me. Okay. So here it's interesting. Some things that jump out to me is the node size. So I think that's saying 8K, 8 kilobytes for each block. I think that's probably the max size they're trying to accomplish there. Now this is a gen server. If you're not familiar with Erlang, I'll explain very briefly. In Erlang, everything happens inside a lightweight process. You can spawn new processes, send them messages. Gen server is an abstraction that creates a particular kind of interaction, which handles managing state as well as receiving messages for you. So all you have to do is write some callbacks that say, hey, when I get this kind of message, then I want to do this. And it's a really, and then there's all this extra stuff that's that helps you with system debugging and monitoring that comes with gen server, and you don't have to implement. So that's why you see a lot of gen servers. Yeah, microservices before they were cool, right? These are like nano services. So gen server is not a server in the sense that it holds open a socket and listens on it necessarily. It could be. But it's more that this is a lightweight process that has a particular kind of interaction that it expects and is ready to handle automatically. So you don't have to write all of your own message handling and deal with state transitions and things. And it also behaves nicely with the supervision trees that Erlang has, so that you can restart something that fails, etc., and you get good reporting on why it fails. Anyway, that's a long-winded way of saying we need to ignore the fact that this is a gen server and see what it's actually doing, because here's what the contents of this is the state that this gen server holds. So it's going to have a file. It's going to have a position that it has written into the file. It looks like it has some accounting things about where was the last node and what was the size of that last node. And then there's this node struct, which looks like a list of keys and the level. So a node, I'm assuming that what this lets us do is, as we write to the file, You start adding things to this node when the members list gets too long or the size gets too big. Then you purge, you don't purge, but you like write that node to disk. But you still keep the data structure around that has the keys in it, so you know, well, if I'm going to point to a particular block of the B tree, and it's interesting they call this node and not block, but a particular block of the B tree, then I can look at the first key in its list and maybe the last key. I don't know how it's gonna work, and then see use that for the inner node that'll be referred to it at a higher level, and so forth. And this expiration value is, I'm assuming, the timestamp stuff. Okay, so name is probably the file name. And then we're tracking a bloom filter. Now, we probably won't do this on the first pass because we're ignoring it when we read anyway. And we need to spend some time figuring out what kind of bloom filter we want to use. And then there's also issues of, can we even read the ones that are written on the Erlang side? I don't know. Okay, so block size is node size. So this is this constant up here, 8 times. So they're looking for 8K blocks. And then compression, we won't have compression on at first. I don't know what the options are. There's probably something in terms of starting up the process. And then it's finally, how many values did you write and how many tombstones? Remember, in this sort of structure, you can't just remove a record. You have to write that it was deleted, and then eventually those will get purged as they go down, as they go into deeper levels. Okay. So, the public API is really pretty simple. You do open, and that starts the process. So over here in our nursery where we're doing open, that's going to link that process to the nursery, or to the process that owns the nursery. And then if this writer crashes, then the thing owning the nursery will crash too. It's sort of a safety guarantee. And then there's, you call add, which casts. So there's two kinds of messages. There's call, which expects a response, is basically synchronous, for lack of a better word. Even though it's not synchronous at all, it's just like send a message and wait for the response. But cast is just like send the message and don't care. So there's no back pressure on it. But count and close are calls. So basically give me the number that were written and then close the B tree. Okay. Now let's start looking at what they do when this starts up. So init is called when the process starts. This is part of the gen server contract. You could also think of it like dependency injection. So you're injecting the contents of your code into a template of how a process works. That's another way to think of gen server. Okay, so here it's going to get this call, which has the name of the file and the options. There's a lot of stuff in here that we don't really care about. Now the option size, I'm curious about where this goes. So size. Okay, so that's the expected size of keys. Aha. So note here that this is using the min level that the nursery has configured. Say this is the size of the B tree. So this is the number of keys that can exist in this B tree. That's what that means. Okay, and then there's the block size, which either comes from the options or from that constant that we defined up above. And this, we need to find where this is. First block position. That's not going to work. Let's find that. And in fact, we need to find define. Okay, so this is right. So this is saying the first block starts at byte 5. Or if you're 0 indexed, byte 4, right? Because you've got the file format marker at the front of the file. Okay. Yeah, so the result of opening this is write the file magic to the file, create a Bloom filter, and then return the struct that contains the state of this process. That's not too bad. We can make like a new function for a writer. Obviously, we're not dealing with processes here, so some of the things won't translate exactly, but we could get to that pretty quickly. And then there's we can look at the individual callbacks. So in this case, they're using a style of writing these callbacks, which is that you pattern match in the function head. So in other languages, you might call it destructuring. There's pattern matching in Rust, but you can't pattern match on... that's not exactly accurate. You can do restricted kinds of pattern matching in the function head of a Rust function. But here it's actually used as kind of a match statement. If you think of a match expression in Rust, this is like, okay, we're gonna have a match expression, but it happens at the level of the function. So this could have been written as, okay, well, you get a message on cast, and then we're gonna do case, message of, and then match each of these different patterns. Okay, so thanks, Chris. Anyway, so they're matching on, is this a tombstone with a timestamp, or is it a regular tombstone? Is it a value with a timestamp? And note here that it's saying if you're adding something with a timestamp that is expired, it's not going to add it to the file. That's kind of interesting. That's probably useful when merging, I imagine. Okay. And then similar with values. So it looks like the guts of this is in append node, right? And we need to look at what those arguments are. But so let's look at append node. We'll skip over handle call and handle info. Obviously, like there's some of these things that's sort of like implementing in an interface or a trait in like an interface in other languages or a trait in Rust. Like you have to implement all the functions, but some of them aren't useful for your particular case. Note that also here on termination, this is like the system's shutting down. You need to stop what you're doing. This will close the file and delete it if it's a non-normal shutdown. Okay. Note that if this is a normal shutdown, since the file is actually a process in this case, you don't need to do anything specific, because the linkage of this process to the file process means that it'll automatically close cleanly. That's a nice guarantee of the Erlang platform. Okay, so let's find append node. Oh boy. Okay, so when you're adding a key, this is interesting. So append node is basically saying, make this node struct and put it in the list in our state. But it's also, okay, so this is, again, they're pattern matching on the head of the function. So this is, if there are no nodes recorded, then take this level and add that node to the listed nodes, and then call again. And so then the next one is, this is a case where, all right, I'm just going to start putting some comments in here so that we can understand what's going on. And let's put it at the end of this one. Are no nodes in the file, create one, and try to add an entry. Okay. Okay, this one looks like some sort of... Okay, so if you're trying to insert a key at this level, and it's at a lower level, so like, you know, you're not adding something to an inner node, but you already have an inner node written. Then you call again with adding a node that it's one lower level than this. Okay, that's interesting. So, but no, this is self-recursive, right? Or tail recursive is the right word. So let's say you had already written an inner node, or you'd started writing an inner node, like, hey, I have a level 2. And we start at level 0, we have a level 2 node already, which means we have 2 levels of the B tree. So it's going to go, okay, well, we need, if this is adding something at level 0, we need to add a new node to the list, which is a level 1. And then we need to call again. And it's still here. So then it's going to push another one on. So you'll have, if you've already, your latest one is 2, and you're trying to add something at like a key at level 0, then you're going to get a level 1, a new level 1 that's empty, and a new level 0 that's empty. And then it's going to come back around and try to match these again. Yeah. Okay. If we are adding a key at a lower level of the B tree, than the latest node, add intermediate levels until we reach the level to be added. Level where this key should be added. So that's interesting. I'm not, this is kind of tickling my brain about what sorts of structure we'll need to create in our writer. Okay. So now here's the one where we actually do the work. Okay. So this would note here that they're also using pattern matching in another way that Erlang lets you do, where it tries to match the entire function head. So that means if you have 2 variables of the same name, that means they have the same value. So in this case, we are adding a node, we are appending a key to a node at this level, and the latest node in our list of nodes also has that level. Okay, so it's an implicit equality. Okay, and then the key and value, and here's our state. So we have the current node and the rest of them. And then there's all the rest of this stuff in the state of this process. So the value count, the tombstone count, and the bloom filter. And this is just saying that the bloom is not already defined. And they don't have another case, so I'm assuming that if the bloom filter is undefined, it's just going to blow up. That's not that surprising. That's sort of one of those sort of invariants that if we were doing this in Rust, I'd like put a panic. You would definitely want to avoid that case. Okay, so then it's looking at the list of members in the node. And interestingly, okay, so in Erlang you build lists backwards. You build them from the tail up to the head. And this is called, in other languages called console, etc. So it's just asserting that you are adding the keys to this file in order. And this assertion is like, if you are adding them out of order, you break an invariant. You should already have them in order at this point. So this is just a check that if there's nothing in the list, if there's nothing written to this node yet, it's just okay. If otherwise there is a key on the head of this list, that the key that we just received is greater than that, greater than or equal to that one. Okay, and then so we have the node size. Okay, so then it looks like they're estimating how much it's going to increase the node size. We may need to look at that function, but I assume it's going to sort of be like our, when we did on entry, we made this function last time, which is encoded size, right? I assume it's going to be like that. Okay, and then right, so then it's like if you're at level 0, add this key to the bloom filter. Which, remember, the bloom filter exists so that you can quickly determine whether something is in the file. And you can get false positives, but you'll never get false negatives. You'll never have to search and go, or rather, it will never tell you it's not in the file if it is. It might assume, or it might go, yeah, it might be in the file. But if it tells you no, you know it's absolutely not in there. Okay. And that's, we don't need to be concerned with that right now because we're not doing the bloom filter. Okay. And then it looks like we're updating counts. So this is the total count, or the tombstone count, and the value count. So if we get a tombstone, if we're adding a tombstone, then we update that one. If we're not, then we're updating the value count. And then obviously if the level is greater than 0, we don't update those counts because these aren't real entries. They're just pointer entries. Okay, and then they're adding the key and the value on top of the existing members. And then updating the node in the list. So this is a sort of thing where we might have a node structure, or I would love to call it block. I don't know why they call it node. And then updating the counts and the bloom filter. And then if the size, so this new size was computed up here. If the size is greater than or equal to the block size, then it calls flush node buffer. Okay. This is probably where the meat of it's done. This is just doing some checks and accounting for the added key. Okay. So here in flush node buffer, this is taking a node, I guess. It's interesting if we might well, let's see what it does. Okay, so it's going to remember that it was adding on the head of the list, so in reverse order. We're gonna reverse this list. Now you'd be like, oh gosh, that's expensive. It's actually not. They're big optimizations in the Erlang virtual machine for reversing lists because it's a very frequent operation. You just don't want to do it constantly. Actually, I worked on one library at one point that we were using a Basho, and we discovered that it was trying to emit things in order, but it needed to build up the list in reverse order. Well, it would reverse the list, add the thing on the head, and reverse it again on every iteration. It was like, you're totally wasting memory. And when we changed that to only reverse at the end, oh my god, the performance increase was insane. It was a protobufs library, by the way. Which it's like, why do you care if it's in the correct order? They're tagged. Come on. Anyway, it's neither here nor there. Okay, so moral of the story is we built these in reverse order. Let's flip the order of the list so they're actually in order now. and then it's calling this encode index node, which I assume is like, yeah, so this is like, it's writing all of this in RAM, it looks like. So this is going to be like loop through the entries and emit them individually, which we already kind of have some code for that, which is nice. Okay, and then it's going to capture, and that's why it does it in RAM, is that it's going to capture the actual size of the encoded, and that becomes the head of the block, right? So this is stuff that we've decoded before. And then the total data size is that, you know, the block size plus the 6 bytes on the front to tell how big the block is and what level it is. Okay, and then it's like, okay, write this to the data file. And here's that bit where I mentioned keeping the keys around is useful. So it's going to take the first element out of the list of members, and that's going to be the key. And then it's calling append node again. So it's saying, okay, increment the level that we just wrote, take the key, the first key in that, and, you know, create a, you know, node position data size, right? So where's that node pos come from? Oh, okay. So it looks like when you create a node, you give it the position in the file, right? So that's already decided, and we probably need to go back up to append node and find that, because that's important. And I suspect it comes from the state. Oh no, this is in the state. So, okay, so we're tracking that, right? And then as we're writing to the file, you add the amount of data that was added to the file position, and then you use the original file position as the previous node and the previous node size. So, okay. Yeah, so note here, this is where we're incrementing the levels. So if we flush a whole node, then we increment the level and start writing a level above it. What's curious to me is if you're writing keys sequentially, right? Like what would this look like? Because I feel like, oh no, actually this is just fine. So let's assume you've written or you're like written out node 0 and one node at level 0 that just contains keys and values, right? And then this flushes, and so you start adding a node at level 1, and it's going to have in it, so let's go back up here. So now you like removed, note that this is basically popping one off the front of the list of nodes. You've removed this level 0 node when you flush it. Okay, and then you have the rest of these. So we might have some kind of like stack or deck that we use for this. But if this is empty, then you're going to go up to this case and go, okay, well, let's add one. Let's add one at that level. And then this case won't happen because level, you know, the level we created here is 1, and the node that we're trying to add is at 1, or that we're trying to append to. And then it'll just put into the key and value, and it won't flush because we just flushed. It will be, you know, nowhere, it's going to be nowhere near the block size, right? And so then it'll just continue. Okay, I think I have a pretty good understanding of this now. There are some bits in here that we haven't looked at in particular. Archive nodes looks like something you do when you finish. So let's look at close real quick. So close calls archive nodes. Oh, that's count. Sorry. Okay, so that's why you're tracking the value count and the tombstone count, is so that you can get how many nodes are in this file, or how many keys and values. Okay, so close calls archive nodes and then basically stops the process. So let's look at archive nodes real quick. Okay, if you don't have any, that's interesting. We'll need to look at. Okay, if you don't have any nodes to write, then you write out the Bloom filter, or you serialize the Bloom filter, and then, hi Isaac, welcome to the stream. I am having a good day, thank you for coming. We're learning about how to write the B trees, which is super interesting. So okay, so creating the Bloom filter, you know, if there is no last node position, then this contains no entries, and so you just write, you know, 0 and 0. There's no Bloom filter and there's nothing in the block, right? Anyway, okay, so then this is where we construct the trailer. There's 4 bytes of zeros, which is interesting, that we saw when we were trying to read the file, right? There's the serialized Bloom filter, the size of the Bloom filter, and the root position. And here we're determining the root position is, I'm guessing this 0, 0 is like block size of 0, level 0. So it's saying we don't have any entries. And then it's just like what would be the default first block position, which is 4 past the beginning of the file, right? Because we wrote the magic at the beginning of the file. Okay. So this is assuming we have no nodes to write. We write the trailer, and we call data sync and we close it, and then we set the state, clearing out some things, right? Okay. So then if we have nodes that haven't been written, it's going to call flush node buffer again, which we saw will do it will, you know, go through all of this stuff of flushing out the level. And interestingly, okay, so then it calls itself. So if we still have nodes to be written, so if we had written a level 0 node and we flush that to disk, and then there's a level 1 node that's still there, right, so this is like, if you have only 1 node left and its level's not 0, then ignore it, because you have only 1 entry in there. Now I don't know what the invariant, like how this maintains that invariant, because I could imagine a case where, I guess if you've written more than 1 level 0 node, you'll never have this case. But I do wonder about that. Interesting. Okay, so I think we've kind of covered most of what the writer does. Let's get into creating our own. We're going to need to think about the structure, and then we can start to take our nursery recovery and, you know, implement the writer for it, and then we will have actually recovered and not just loaded things from the write ahead log. Okay. Yep. Okay, so we do have that encoded size. That will be a huge help. Let's make a new module. called writer. And then we're gonna have to put this in our main writer. And I don't like how, I guess it doesn't matter. I was gonna say I don't like where it put that, but whatever. Okay, so we need to, we're gonna have to use create format. I'm gonna say star because I don't know exactly what we're gonna need there in all cases. And let's use create error star. The other thing we're gonna need possibly is we need to think about how to I guess this isn't, we need to think about how we're going to write, because I feel like not error, we've kind of taken a different route here. Maybe what we do is create entries, so you're never adding key value, you're always adding entries. Right. Yeah, I think that's what we should do. So the writer will take entry structs rather than separated key and value. That probably makes most sense. And then we can possibly use we can use whatever we want as far as like the contents of each node. Remember over here when it's adding the key to the node, right, it's just putting it in memory. So I don't know that there's any reason why we couldn't just put entries in here. It's essentially what they're putting in this list. The other thing here that I might want to do real quick is make an accessor for key that will match over the entry here, because we're going to need that for creating poslin entries, right? Okay, pub create key self, and we'll give a u8. And it's basically going to be the same thing in each one. We can probably combine these match arms, actually. Let's do that. And I know it looks like a mess right now, but the formatter will help me out here. Okay, now it's probably going to be like, yeah, it's immediately dereferenced. Can we just do a slice? That's the proper way. Okay, so this will let us get the key from the entry really easily when we're in the writer, which will mean creating those inner entries will be a lot easier. Okay, so we need to emulate the block. And since I was so annoyed that they called it node and not block, let's call it block. So let's make a block. Okay. The interesting thing here is, Does format have a block? Format has a block, so we need to maybe not import everything. We need entry for sure. Which kind of raises the question in my mind. Yeah, this is for a different purpose. It might be confusing to name these the same thing in different modules. The thing is, this, I'm not intending to expose this outside this module. It's not even going to be pub crate, so I don't think that there's going to be a problem. It just might be a little bit confusing. Okay. So let's go up here and look at the definitions. So there's a level. There's the list of members. And then there's the size. Now we can they're using a list, a flat list, and then having the invariant that the key that's being added is always greater than the last key, greater than or equal to. That's so that you don't have to have some kind of more complicated data structure here, which makes me think we could use a vec or a deque, D-E-Q-U-E, deque. Or we could use a B-tree map. And the B-tree map would ensure that we're in the correct order. I feel like the B-tree map is the easy solution here. So let's go ahead and use that. B-tree. We use B-tree. I actually don't know that we can guarantee the binary heap, max heap. That's not what we want. Let's use B-tree map. So we need a level, which is in the case of our format vecdeq. Yeah, I mean, the first time I saw that data structure, I was like, how do you say that? But the person presenting, I think it was like, I don't know, it was on some like Ruby VM internals or something. They called it a deque. So I don't know. It's like LaTeX versus latex. It doesn't look like it should be called LaTeX. Anyway. Okay, so the level and a size. What we need to know is should this be a U32 or a U size? I think based on the format, let's go down here. It's a U16. So let's make it a U16, and that will ease this part for us, so we don't have to do as many coercions. So we'll do U16, and yeah, and then size we can use U32 or we could use U size. What's interesting to me is I think that we're returning on format for entry. I think we're returning U size for encoded size. Yeah, so let's use U size there, and then we'll really don't like it, but we will coerce this to a U32 when we write it out. Okay, size is a U size, and then let's call it members just to be consistent, and we'll make this a B-tree map of this is going to be a vec U8, the key, and then entry. I wonder if we should just go through like this. We're going to have to clone the key in order to get it. You know what? Let's do it the hard way first. let's make this a vec of entries. And then what we'll do is we will either ensure that it is sorted on every insert, or we will do like a sort by type thing at the end. Okay, so we have the struct defined for each block, and then we need the writer struct. And now here it's called state, obviously because it's the internal state of a process, but we're just going to make it a struct. And even if we're not using all these things, again, I'm probably going to have to put allow dead code on basically this entire module. But we're going to put the compression in there, and we won't need options, but we'll need these things. And we're not going to bother with a bloom filter for now. It's going to come back to bite us for sure. Okay. So here, struct writer. And what do we need in it? We need the file. So we will use we'll probably need more things there. So if they're calling it index file, let's call it index file. And then we need index file position. Interestingly, I think this is going to be a U64 because in the or it's usize, because this is really about how far we've gone into the file. And then down here, when they write the trailer, yeah, it's 64-bit. So we might as well use a U64 there. We'll have to do conversions at particular places where we're incrementing this, because we'll have to go usize as U64 and add it to this. Not great. Okay. Going back up here, we'll have last node position is going to be another U64. Last node. Last node size, and here we can use usize because we were the block, right? Nodes, we're going to have, this is where it might make sense to have a vecdeck, because we're going to want to be able to make that stack thing, right? So vecdeck, vecdeq. So this is going to be a vecdeck of block. Okay. Name, I guess that's the file name. We'll skip bloom filter. Block size. It's interesting, this is, I think, pretty much everywhere default except for options is passed. We should see if that is ever passed in this code base. So let's search for HanoiDB writer open. Oh, it is passed, right? Oh, no, wait, this is the total size. Looking for, yeah, they're not, here they're just messing with the block size in a test. Okay. let's just assume this is a constant, and let's go ahead and make it up here, right? Because this is this node size, right? Okay. So then we don't have to carry that. That would be useful for testing robustness, but that you don't have something in your code that accidentally depends on this block size, but I don't know. Okay, and then we need compression. Which we're not doing anything with yet. And then we have value count, which is going to be usize, and tombstone count. Okay. All right. So that's the majority of the stuff that we need to have in here. We, considering what terminate does, we might want to implement drop on this. I suspect, though, if the semantics of dropping a file is to close it, so we might not need to do anything there. And we should probably explicitly close regardless. Okay, so let's make the constructor. And what is it going to take? It's going to take a name. So it's going to be a string. And we should probably do result of self here, because we might not be able to open the file or whatever. Where's this do open? We need to look at that briefly. Okay, so this is like doing buffered writes. I don't remember what all of these things are, but it's basically saying give me a 512K writer. Maybe we should do, instead of file, this should be like a buffered writer. The thing is, though, if we do buffered writer around the file, let's see if we can just open it with a buffer reader. Can we do open options with something like that? Append. I think the exclusive was so that you couldn't, on Erlang specifically, so you couldn't open the file twice. Like, it's only owned by this process and nobody else can write to it. Nobody else can send messages to it. I think that's what exclusive means. Yeah, there's nothing here about we should probably just use file create. That's the thing also too that we can probably ignore for now, because I think that option in here is about we'll need to look at this function real quick, but I think this is about performance tuning. So it's like how much do you want to have pending in a write potentially? Okay, so they're opening it in append only, which makes sense. Let's look at that index file name. real quick. Oh. You just gave me an identity function. Thanks for the misdirection. I suspect that probably what happened was in an earlier version, they had some kind of naming scheme that was enforced here and it wasn't the full name. So that was funny. Okay. So basically we just need to open the file with append only. So we're going to need open options. And let's go back up to where it inits. Okay, so right. We're going to say let index file is going to be open options new append true. I don't remember if you need write true. We'll just do write true. I think create new true. So like we need to make sure that it doesn't exist. Open options. Okay, so we don't need to do write true, append true. Just append true is sufficient. Okay. And then we'll do open name. Okay, so this question mark. Okay, so now we have the index file. Which is a file. Let's pretend that we can construct this just so we can get that out of the way. So we have index file. We're going to write the magic to the file. And here's a part where I'm kind of on the fence because we can't create the bloom filter. And I'm gonna go ahead and put that in here as a commented out field. I don't know what that's going to be called, right? But because we can't write the bloom filter, I'm a little bit hesitant to use the same like file type marker as we do in this file. Note that we check that it's this. But if we want to be able to read it back after we've written it, I guess we're currently ignoring the bloom filter. At some point we're going to have to get off of this just emulating what Erlang is doing, the Erlang code is doing, and actually like own it and say, well, we'll emulate what it's doing, but we're not going to rely on the fact that we're using, you know, a bloom filter that was written in Erlang. Like that doesn't make any sense. We might want like a surf or something, like I mentioned before. Okay. Okay, so we're gonna have to do these things. Let's do index file write, and we're just going to do this. So we need mute there. And we need question mark. Write all, excuse me. Okay, so now we can go we're at byte 4. Let's look here. I think, yeah, that needs to be a positive integer. And what are they doing at the beginning? This has no default. That type is wrong then. If they're not, yeah, I think we need option here. It's gonna cause us some pain later, but these can start as none. I think that makes sense. None. Default. Compress, we'll just say compression none. And then if we go and add another compression type later, or we like implement one of those compression types, we can let that be passed as an option. The other thing we could do is say like with compression as a constructor, and then just have new call that. Okay, and then value count is 0 and tombstone count is 0. It's interesting to me that this, and maybe they just didn't run dialyzer on it, but it never caught that we weren't, that like the code does not assign these two. They might be undefined. But the Rust compiler will be like, hey, you can't just leave that. You need to assign it the right thing. Okay. And yeah, we're keeping block size constant because it's not ever changed in the code except for a test. Cool. Right, so now we have a constructor. Obviously it's like doesn't do anything. So we need to implement, you know, add and count and close. Let's implement count first because that's the easiest. Count self. And this is going to return a usize, right? Self dot value count plus self dot tombstone count. Okay, that's exactly what this does. So we can't really implement close yet. We'll need to do this archive nodes thing. Maybe we should hold up on that. And let's start looking at add. So self, and this is going to take and let's see here. Right. So we'll have an internal thing that does append node. Excuse me. We won't be able to do it recursively, which is going to make this really interesting. We might need to have like a loop with a termination condition. But like this lean, like as we saw earlier, this leans heavily on tail recursion and pattern matching in the function head, which we cannot. Okay, so this is no reply with just updating the internal state. So this isn't going to be mute self, right? I think what we're going to do here is it's going to be a result of unit. I don't know if we'll need to return a result here, but I feel like in my gut that there's potential problems here of, well, we tried to write to the file, but some like IO error happened, or there's some internal state that didn't turn out right. So having a result of unit is probably the best option here. And we'll just say okay there for now. And it's going to complain because we didn't use entry. But what we will probably want to do is have a hidden function similar to this, like append node, and pass it the level and the entry. Let's say let's call it self append block, because we're calling it block here, and it's going to be level 0 and entry, and then we'll implement that. Append block. This is mute self. Level is going to be, what do we say, U16? And entry is going to be the entry. And this will return a result of this. Okay, so I think we need to kind of look at what append node does here. There's a question in my mind about whether we looking at this nodes, we have a vecdeck of block. We need to kind of deal with the dispatch thing that happens in append node at first. So we need to look at the nodes on the current writer, and like if there's one, now obviously we're using this like a stack, so we'll want to push on the end. We won't want to pop necessarily unless we're actually writing that block, but we will want to like either take a mutable reference to the last thing in the stack, the top thing in the stack, or insert a new one and get a reference to it. The other thing is that we have to check the level, right? So if the level is not equal, then we need to loop over the level until it's, equal to the level of the thing we're trying to add. Okay, a lot of concerns there. So I feel like maybe we should make that a separate function, and say let's say block, and this is going to be a mute block, right? That's what we want this to be. Let's say self dot the thing is, this says append block, there's an append node. What you want to do is append to block, right? Like, it's not actually, it may add a new node here, and this one is just called append node, but like the goal of this is to append this entry, key value entry, to a node at the correct level, right? Let's see if we can get this function, right? So I want to do get block at level, and we say level, right? And then this is going to be the probably the hard thing, where we figure out, do we need to add things until we're down to this level? Are there any in there? If not, then we need to add one. Like that logic that is kind of intertwined in this function head dispatch stuff. We want to get rid of that and not worry about it. That needs to be like isolated from the work of adding a single key value entry to the node that's at the correct level. Okay, So let's say get block at level, and ironically this needs to be mute, right? And level is U16, and this is going to be mute block. Okay. We might get a better name for that. Okay, so let's see. Let's handle the easy case first. So if what do we call it? We call it nodes. What do we call it? Nodes. Oh my goodness. Blocks, please. Okay. Blocks is empty. So I want to do a shortcut case there. So what we want to do is self.block. We want to create a new block, right? Can we derive the default for that? Yep. Let's do that. That'll save us some time. Okay, so if it's empty, we want to push back, right? And then we want to, right, I know, okay. We want to return self.blocks last. Is there a last mute? Vec deck. Honestly, we could use a vec for this. We're not going to need to pull from the front, but yeah, there's back mute. And we can unwrap here because we just pushed one on, right? Yeah, at this point, maybe I don't need the vec deck. I mean, I just need a vec. Let's simplify it. Fewer things. Okay, so we don't need push back. We'll just need push. Last mute. Unwrap. Okay. So what do we got here? What is wrong? Yeah, it may be missing an else. I know. So if it's not empty, right, I know, it's fine. Okay, so now we need to deal with the case of it's not empty, and we need to potentially let's do it the dumb way first. I'm kind of struggling to structure this, so I kind of want to just get a little bit of the the logic done. Else. Yeah, why am I doing it that way? I don't need let else. We know at this point that there's going to be some in there, right? And we'll put the, we need to check the level, right? So let's do this. This will let us change it. And why don't we say while last block dot level not equal to level, or greater than level, right? This is the part where we are adding new, in this case, new nodes until we get we get one that's at the level that we're trying to add a key to. You know, again, we talked through the case where you have a level 1 or a level 2 node in there, and you need to add a new key at the bottom level. So you keep decrementing. You're like, okay, so there's going to be a new level. If it's at level 2, it's going to be a new level 1 node, and then there's going to be a new level 0 node. And as you fill up the level 0 nodes, then like the keys get added to the level 1 node that's before it as they get flushed. And then when that level 1 node gets full, it adds its key to the level 2 node, and so forth. Okay. We're going to do stuff in here. Okay, so what I'm going to do here is I'm going to say we're going to do push, right? And this is going to be level is last block dot level -1 default, please. Yeah. And we'll do last block. I wish there were a better pattern for this. Last block equals self dot blocks dot last mute dot unwrap. It's probably, yeah, we got mutable borrows twice. So maybe what we do is go, rather than doing this, what we do is we return this at the end. And we do something here. Interestingly, we're doing this here as well as maybe what we do is do else, do this stuff in here, and then we always return that. So we're basically ensuring that there's, yeah. Okay, so now we need to figure out what this is. And then we don't do this. Yep. Okay, so then we solved the overlapping mutable borrows thing. We needed to borrow immutably just to get the level. We could do just the level, right? That's probably even better because that's copy. maybe it doesn't make a difference. Probably optimized out anyway. Okay. All right, let's talk this through. Okay, if blocks is empty, then we push a block on with the level requested. Easy enough. If it's not empty, then we, as long as the level of the last block in this collection is greater than the level we're requesting, we need to push new blocks on, decrementing by 1. It just occurred to me I can probably combine this into the head of this while, but eh. Or it could do it as a 4 with you know, a range. Okay. This is good enough for now. I might put a to do in here and go like, can we make this clearer? All right. Okay, so now we've got a block at the current level. What do we do with it? So we need to look at the entries, right? Append to block. We need to make sure that the key of this new entry that we're adding is greater than or equal to the last key. So we'll say if let sum entry, last entry, let's say, yeah, with this if let you can't put another if here. And there's no let chains, right? Except on nightly. I don't know why. It's like taken years to stabilize that. Anyway. Okay, so if this entry, if we have an entry at the end of the block, members, last, right? So if the key is, how do they express it? Right. So if this key is greater than or equal to the entry key, yeah, let change Sunday. I know, I wish. Then we want, here I would say, since we're going to need results anyway, I think it's probably good for us to make a new variant of this rather than panicking. Panicking is probably valid at this point because it's like exit, blow up. But since we've already conceded to returning result here, we should probably return a result. So return error, and then we're going to make a new error. Let's see. Not any of these. Okay, so let's make a new one. Out of order right is what we're going to call it. And let's just name it that. And we don't need to like put any other goop in there. Okay, so that'll help us bail early if they give us a key that is out of order. Oh, I forgot. These are right. Okay. Actually, this needs to be greater than, because if the check here is like you can have duplicates of the same key. I don't know why you would, but there's a potential that the order that you're writing it in, you write a value and then you write a tombstone, or you write a value, you write a new value, and that's fine. Okay, so now we've handled that. So we need to figure out what the new size is. And we will say, now here they're going, we need to look at this function, I think, estimate node size increment. It's interesting that it's passing this and not using it in any of these versions. So, okay, so what we're going to do is we're just going to use the encoded size thing. You'll see some recognizable values here, like the 9 bytes that we need for the header of a key value entry. Well, the header and the trailer, right? Okay, so we'll just use encoded size. Self dot so this is node size. This is the size of the current node. So this is block dot size plus entry dot encoded size, which means we need to expose that to the crate. Honestly, I'm making things harder on myself by just doing all this pub crate everywhere. Encoded size, right? Okay, so now we can estimate that. We are going to skip the bloom. So to do update bloom filter. Okay, and then I'm tempted to go here. We don't have that in here, so let's cargo add derive more, if I can spell. And looks like that has everything turned off. We're going to want is variant. Yeah, it's not finding it because I don't have that feature turned on. So is variant, is that what it's called? Yeah, this is a great crate, by the way. If you haven't looked into it, it helps with a lot of stuff, especially around enums. Okay. Is variant. There, now it's available. Okay. So over here we can go. Oh, it did hit 1.0. Nice. Oh, I see that. Cool. Yeah, it's a great crate. I've loved using it. Um, so what they're doing here is updating the counts. Um, Now we could potentially just match on it because we want to check. Oh, right. That's fine. Okay, so we could say if I kind of want to do the thing like update all this stuff at the end, sort of like they do here, but maybe that's not necessary. Let's go. Let's just add that. So if level is 0, right? So we're only adding tombstone counts or value counts, and then we'll say something like if entry dot is deleted, then we'll do self dot or block no self dot tombstone count plus equals 1. Okay, is key value. Honestly though, this is a bit superfluous because we'll only be adding poslen entries to things other than level 0. So let's just remove that bit. Value count plus equals 1. Okay. That's pretty simple. And then it's like put this entry in the list. So do block dot members push entry. And maybe what we need to do is do this up here. Right. And the thing is, new size, honestly, this is going to be block.size plus equals entry encoded size. I don't know. Let's put it up there because this takes ownership. Okay. Now what are you complaining about? Yeah, overlapping burrows. Okay. Then let's do that up here. Now still complaining about overlapping burrows. How can we resolve this? The issue is we don't want to mutate this. Actually, what we can do potentially, can we scope this such that this block is dropped? But we don't have to clone entry. Okay, here's what we're going to do. This is dumb. But we're gonna do it. This feels similar to the thing when we were doing Berkeley DB, that I had issues with the overlapping borrows in some loop, and by making a new local scope variable, then I didn't have to be concerned with that. And here we can do, since the scope, the lifetime of this block can be now set to here, we're not going to refer to it after this, we can go self.tombstone count, tombstone count. Okay. Then we resolve that lifetime issue. The things we do for memory safety, I swear. Okay. So now we probably need to have that new size be tracked. Now I removed it, right? We can put that up here. And let's do that here. Because this will be the part where we decide, do we want to flush this block? And this is not right. This is a new size. And yeah. Let's put that there. We might need to, if we get to eventually adding the bloom filter, the surf or whatever, we might need to put this in a different spot. Okay, none of this is returning a result yet, but what we can do here is say if new size, block size, then we'll want to do flush node buffer. And here's another thing where we know that making this call could trigger another flush node buffer. It's not likely because we know that this is like, hey, we're gonna, this is a full thing at this level, so we're gonna go ahead and create a node that's at a higher level. Maybe we don't worry about it right now. Let's call it flush block buffer so it's similar enough. And we will make this do question mark, right? Because what we want to do here is we want to pop off the latest node. We'll write the data. So there's a file right in here. That's the part that needs to be able to return a result. Right? And let's just assume it does that. Except it's not. It's going to return append node or append to block. But let's get there. Let's get through this. I'm kind of running up against the time limit, but I feel like we're close, right? I want to get us through this bit, and then we can close it out and pick this up next week. We might not get to the spot where we can write the contents that we read from that nursery log into a data file, but we should try. Okay. So we don't need to worry about this. We've ensured that they are written in order. And we'll look at that again. I think, you know, that's not actually that hard. I feel like it's the same dang thing as what we did in writing the nursery log. So that'll be easy. We just need to know how much we wrote, so we can write the header of this block. Okay, so we'll say let block self.blocks.pop, right? So we're going to pop it off the end. And again, this is taking ownership, so it's going to come off of that collection. And this is, and we should do, unwrap here. Like, I actually don't like doing unwrap here, but I feel like we should also maybe we'll just say expect, and we'll say cannot flush block that doesn't exist. I don't know that that's useful, but like returning a result there in a case where our algorithm's just messed up, it doesn't feel good. Like, and honestly, we should never be able to hit that, because if we just added something that caused us to flush the block, because the new size of the block is bigger than our, or you know, greater than or equal to our maximum block size, then like it exists. Oh. All right. Anyway, yeah. Okay, so let's look real quick at what they do here. Encode index node. I'm pretty certain it's, you know, we could derive it from what the, yeah, so this is just picking the thing, and you like write a tag on the front, and then you encode each of them, and then you potentially compress it, and that's what you got. And you've got the compression on the front. Yeah. Okay, so that's kind of what we expected based on, you know, this stuff, what we'd expect here. And you've got the compression, you've got the tag byte, and then you've got the individual entries. So we can do that. We are not going to compress, obviously, but I should make sure that we can get that compression thing as a U8. Yeah, I did repr U8. We should be able to take whatever it is and go as U8. That's not a big deal. Okay, so we need to okay, so we took the block, and then let's make a buffer as a new vec. The thing is, actually, we can do with capacity here, because we know the block dot size, and then we know that we need 2 extra bytes. We need the compression, right? And I'm sorry, we need more than 2 bytes. We need, so we get the compression and the tag byte, and then we also get 6 more bytes. So let's just do +8. So that's block size plus level plus compression plus tag end. And then from format, we also need, we need those constants. Are those in there? The top? Yeah. We'll make that pub. Yep. Okay. All right, so now what we can do is we can I want to reserve these 8 bytes at the front. So let's create 8 zeros, right? There's probably a more efficient way to do that. So let's say reserve space for block size, level, and the thing is, though, we could probably fill it with zeros and then go ahead and put the level in there and the compression and the tag end, and then come back with the block size. The interesting thing is, yeah, it's block size +2, so we could even write this before we know, because we know the size of what it's going to be written as, right? They're kind of doing this in reverse, but we've, you know, with our entry like encoded size being tracked as we add things, we just know. So let's not do that. Let's just write it. So we're going to say extend, and this is block.size +2 as U32 to VE bytes. Right, and then we'll also extend with block.level to BE bytes. Okay, so we've added the block size and the level. And then we'll buffer push self.compress as U8, and we'll push tag end. Okay, so there's the header of our block. That was actually turned out really nice. I wasn't certain about this because the code in the Erlang is very much like, well, write it out and then compute the size. But we've, you know, maybe they felt like this was just an estimate, but like we got pretty accurate sizes of entries in our implementation on the Rust side. So like, why shouldn't we take advantage of that? I think maybe the issue is that you don't know until you've compressed, but which we should maybe put a caveat here. Regardless, oops. Yeah, let me put this above, and then it won't reformat that weird. Regardless, we know that like the maximum size it could be is uncompressed. So, the question in my mind is, do we just reserve those and then update them later, like we did with CRC32, or we just leave this to do for now? I think we leave the to do for now, and then when we get to actually implementing compressions, um, we can flip that around and just put the 8 empty bytes. Except it won't be 8 empty bytes. We'll make 6 empty bytes, and then or 4 empty bytes, and then the level, and then the compression, and the tag, and then we'll compress the whole thing, and then we'll go back and update the size. Okay. All right. This felt like it was way more complicated than it should be. Um, okay. So we know. So now we need to loop over the entries. And then we're just this is gonna be like super simple, right? I need to, no, I know that we added the tag at the end. So we just do buffer extend entry dot encode. That's all we have to do. Okay, so now we've encoded them. Except this won't be like, when we get compression, it'll be like we create a compressor, and then we extend the compressor with the entries rather than this flat buffer. Okay. So now we do self dot, and they're not doing data sync here. That's interesting. I think that's probably okay. So then we do self dot file write all buffer, and this needs a question mark, right? Because that returns a result. Does it not? It should. Okay. And then we need to call pen node again. We need to track some things here. And this is adding a posilon entry, right? So let's figure out what those things need to be, and we need to do this sort of thing. Okay. Okay, now we do our accounting. The thing that bugs me here about that being option, I feel like this should be filled with No, okay. So this is going to be sum of the index file position, right? Oops. Last node size is data size. Sum of buffer.len. I think that's probably what we do. And then we go self.index file position. So we're just adding to what the original index file position was. And we'll say a buffer.len as u64. I don't know. I'm wondering if this is this is like useful to have as u64. I'm not sure. Okay, so then we've modified those things. I think that looks correct to me. Okay, and then what we're going to do is we're going to call self.append to block, and here it's going to be level +1. And we need to make an entry pause len of block position. So we need to maybe just do let block pause equals this. Block len is buffer.len, and then we can put those in here. Oops, if I name them correctly. Okay, and then here we do block len as u64. And this is a U size. This is U64, this is U32. Oof. We're fighting with we're fighting with the encoded version versus the in-memory version right here. Anyway, eventually we'll figure this out. Okay, so let's just do that, and this is going to be wrong, but it's going to, so it'll complain. And then key, what we need to do here is let's do it up here. First key, block.members first unwrap key to owned. It's a long way of saying give me that as evacuate. Okay, so block.level. Okay, so I think I'm concerned about these conversions. This one, not so much. Because you have 64-bit machines, a U size is going to be a U64. They're like the same type, basically. It's just the context within which they're used is different potentially. This, I feel like we can't safely coerce this, except for the assumption that it's never significantly bigger than this, because that, you know, that easily fits it within a U32, right? I don't know if there's a way to do, it's like we could do try into. Let's see, let's look at U size. And it's another case where I'm worried about, like, should we panic or should we return a result there? I feel like we should panic. Come on, where's the try stuff? It's all the way at the bottom after all these bit shifting things. Okay, there is a try from, right? The error is try from int error. And then did we wrap that anywhere? No. And honestly, I feel like we should panic in this case. So let's, rather than, let's do that. That'll make me feel better. Like that one I'm not so worried about, but this one, right? Because if it doesn't fit, then we can't write it. So why should we do anything? If it doesn't fit in those 32 bits, right? Okay. So yeah, we are recursive. I don't know a way to not do that in this case, except for having a different implementation that basically does this. Okay. Wow. The only thing that we haven't done so far is to do the cleanup. But I think that, like, I'm getting a little tired and this is probably a good place to stop. So here we have the to-do MD, and yeah, interestingly, we don't care about the fan out of the B tree. It's based on size. Okay, so let's update this. What we're going to do is we need to write any pending blocks on close. Right, so we need to implement close, and we need to write any pending blocks that are still in the writer. And then what we're going to do is write nursery.data when we recover the log, the nursery log. And my cat is wanting attention right now. So it's also another good time to stop. Another good reason to stop right now. Okay. Oops. Yep. And we're going to add writer.rs. And we don't care about that. Let's look at lazy git because it'll make it friendlier. Okay, so we added that. And we added some things there that should make it easier on us. We added that module and we added the writer. We don't care about the cargo lock. We added that. And okay. So this is session 6. Add B-tree writer. And we still have to do the does not yet archive. Please don't mess with my microphone, kitty. And she messed with my mouse too. That was fun. Where are we? Give me focus. Oh, did it? Yep. Okay. So much for that. Okay. Let's just write it here because she borked that. I couldn't fix it. Okay, so session 6, initial. We'll say initial B-tree writer, and let's push that. And there you go. Thanks for sitting through this with me. I hope you enjoyed writing some database. It's interesting, I think, because there's a lot of intricacy there. Obviously, when we did the nursery log, we kind of set ourselves up to make a lot of these things easier by encapsulating that, with the entry knows how to write itself to a buffer. It knows how much space it's going to require, and that made things easier for us in a lot of cases. But then there's also the issue of writing the B-tree file is a very different pattern than writing the nursery log. Nursery log is just splat all the entries to disk. But that's not what happens on the B-tree file. You kind of have this staged thing where it keeps building up. It keeps building up entries, and then we'll add something to the next level if it's building up multiple levels of the tree, and kind of understanding the state of that is tricky. Anyway, I won't blather on any longer. Thank you for coming to the stream, and hopefully see you next week.